All right, so this is an example from 7.2. Planning for college. The superintendent of a large district wants to know what proportion of middle school students in her district are planning to attend a four-year college or university. Suppose that 80% of all middle school students in her district are planning to attend a four-year college. The district has 2,000 students in the population. The type of measure is the 80%. So it says 80% of all 2,000. So that is a population proportion. It is a parameter. It is P equals 0.80. So I'm kind of putting more than I need to there, but basically it's a population parameter. Suppose the superintendent takes a simple random sample of 125 kids. Describe the sampling distribution of sample proportions. So we're going to describe distributions by cussing. I need to describe the distribution of my p-hats. So the true proportion is 0.80. I'm taking a sample of 125. All right, let's do it. Number one, center. So the center, and you can go back in the notes and look at this if you want, but this is the center, this is the spread, this is the shape, it's going to kind of be, all going to kind of look the same. So the center, the mean of my p-hats, is going to be the true population mean, which is going to be 0.80, and then check the condition. That's going to be true as long as we took a good random sample. She took, I guess, an SRS. Check it off. Spread. So the spread is going to be the standard deviation of my p-hats, which is the square root of PQ over N, which is the square root of 0.8 times 0.2 divided by 125. Remember, Q is the probability of a failure, so 80% success rate, 20% failure rate. So we'll type that into our calculator. 0.8 times 0.2 divided by 125. 0.0358. 0.0358. And the condition for that one, you need independence in order to use this formula. That is the 10% condition. So to check it, we simply need to say our sample size, 125, is less than 10% of the population size. The population size was 2,000. And that's true. 10% of 2,000 is 200, so we're good. And I talk a lot about this in class, but why is this number important? How do we interpret this number? This is the standard deviation of our p-hats. What that means is, remember, standard deviation is the average distance from the mean. So this means our p-hats are going to be, on average, 3.5 percentage points away from the mean, which is the true value. So our estimates, our p-hat estimates, are going to be, on average, 3.5 percentage points away from the true value. That's why this thing is important. And shape. Approximately normal. And how do we know? We check the large counts condition. By the way, these are all going to check off. N times P. That's 125 times 0.8. I don't know what it is, but it's bigger than 10. Check it off. N times Q. This one's going to be closer, but 20% of 100 is 20, so that's still going to be good. So there we go. That's our distribution. What is the probability that the sample proportion superintendent gets from this one sample is within 5 percentage points of the true proportion? So what's the probability that her p-hat is going to be within 5 percentage points of the true value? The true value is 80%, so what's the probability it's going to be between 75 and 85%? Well, luckily, we have a normal distribution that is centered about 0.8, has a standard deviation of 0.0358. I want the probability that it's between 75, and 85. So I want that area. Because it's a normal curve, I can calculate it. Menu, statistics, distributions, normal CDF, lower bound, upper bound, average, standard deviation. 83.7%. So there's an 84% chance that she's going to be within 5 percentage points of the mean. Now, if that's not good enough, if she wants she wants to be more assured that she's going to be within 5 percentage points, then she's going to need to kick up that sample size. She kicks up that sample size, makes this number bigger, makes this number smaller, tightens up this distribution, and now she'll be more likely to be than 5 percentage points. That's the advantage of taking larger samples, right? As long as they're good samples. Okay. How does quadrupling the sample size change the center? Well, the center is only dependent upon the true proportion, so that doesn't depend on the sample size. So center will stay the same. The spread is going to change. The standard deviation is calculated with this n on the bottom. So if you quadruple the n, that's going to give you a factor of 4 inside a radical larger on the bottom. The square root of that 4 is a 2, so we divide by 2. I'm going to cut the standard deviation in half. So a factor of 4 will cut the standard deviation in half. And the shape's going to stay the same. Okay. All right, that's 7.2.